Hi, welcome to the Easter exercise of Chem 2005. I will resolve all the exercise, giving an explanation of how it's working and how we have to resolve this exercise. The first question is about if these hetero compounds are aromatics or not. And we will start from the first. Here we have 2, 4, 6 electrons plus the 2 electrons of the nitrogen. That means that we have 8 electrons. Remember, if the 2 electrons of the nitrogen we don't consider that are in the p system, what we have is that the nitrogen is not in the p system, the p system is disrupted, and then it's not cyclic, or we don't have in all the compounds, in all the atoms, a p system. That means 8 electrons, following the Huckel rules, is not aromatic. Next one here, what we have here is a carbon with a sp3. Obviously here we don't have the p system is disrupted, means non-aromatic. Here what we have is 2 electrons of this double bond, 2 electrons of this double bond, and 2 electrons of the oxygen. Because we are forming a carbon-nitrogen double bond, the pair of electrons of these nitrogens are in a sp2 orbital, because the pz orbital is used to form the double bond. That means doesn't count. We have 2, 4, 6 electrons. This compound will be aromatic. If we go for the following one, we have 2, 4, 2 electrons in this nitrogen, 2 electrons in this nitrogen. This will lead us to 8 electrons. Will not be aromatic. Okay? And finally, this compound, we have 2, 2, but if we check this nitrogen, this is a sp3 hybridized nitrogen. That means that it's not part of the aromatic system. This compound is non-aromatic. Okay? Good. Go for the second one. The second one, basically what they are asking is order in terms of basicity these 3 compounds. Okay, we have these compounds, imidazole, pyrrole, and quinoline. Okay, we can check which of these nitrogens are basic. That means which of these nitrogens has a pair of electrons available to take a proton. Okay. If we analyze the pair of electrons of this nitrogen, are not part of the p system, are in a sp2 orbital. That means that these are available. These 2 electrons of this nitrogen are part of the p system, are in the pz orbitals. That means that are not available. That means that this first compound will be basic for this nitrogen. Second one, pyrrole. The pair of electrons of the pyrrole, because the pyrrole is an aromatic ring, are not accessible, are in the pz orbital. That means that not available. That means that this compound will not be basic. Okay? Finally, the isoquinoline. the pair of electrons of the nitrogen are in a in a sp2 orbital, okay? That means that are available. Clearly, the less basic is the pyrrole. Okay? Then, these two compounds, the imidazole and the quinoline, are basic. Which is more basic? Well, in order to make an easy decision, what we will do is to protonate okay, we have acid. Okay, the pair of electrons of the basic nitrogen will take the hydrogen, and what we have is this compound. Okay? But now, in the case of the imidazole, what we can do is simply a resonance form. That means I can put this pair of electrons here, and this pair of electrons can go to the nitrogen, and I can get that means that when I protonate the imidazole, I have two resonance forms that stabilize the positive charge. That means that these will increase the basicity because the conjugate acid is more stable. If we protonate the quinoline, we cannot stabilize this positive charge. I mean, the positive charge will be in the quaternary nitrogen, and that's all. There are no resonance forms that stabilize the compound. That means that a little bit more basic than the pyrrole will be the isoquinoline, and the more basic will be the imidazole, because we can stabilize the conjugate acid with a resonance form. Okay, that is the reason why the most acidic will be the imidazole. Okay? Some exercise, what we have. We have this aldehyde, and we treat it with this amino ester. What will happen in triethylamine and ethanol? Well, basically when we are doing this type of exercise, what I recommend is to check what are the functionalities that we have. Here, what we have is an aldehyde and a ketone, and here we have an ester and an amine. Basically, the reaction that we know how to do is with an aldehyde and amine. What we can do is the formation of the imine. Okay? We have this imine, and then what is happening, or what could happen, is that we have here a hydrogen let me put the okay. What is happening is that this hydrogen is very acidic. Okay, when we add ethoxide, we remove this proton. Okay, we remove this proton. We generate a negative charge here, and then simply, this is a nucleophile, we have an electrophilic position in the ketone. Right, sorry. What we have is the aldol intramolecular aldol reaction between this anion and the ketone. What we get is this compound that can eliminate, okay, basically, because this is a aldol reaction in basic media, but we will have that we will deprotonate this hydrogen here, okay, and then simply E1Cb, and we generate this compound that basically what we can do is do a tautomerization, and we get the sorry a tautomerization imine enamine to form the final pyrrole. Okay? That means how we face this exercise, we have to check what reactivity we can do with the functional groups that we have in the starting materials. Here we have an aldehyde, here we have an imine. Basically, the typical reaction that we can do is the formation of an imine, and then simply with base, we remove this proton and we form the pyrrole. Next one, what we have this compound. Okay, and we treat this with HCl, water, and methanol. What could happen here? Well, again, we check what functional group we have. We have an ester, we have a ketone, and we have an acetal. And the reaction conditions is acid media with water. The first thing that we can think is that basically we can remove the acetal. We can do a hydrolysis of the acetal, and what we will get is this diol. Okay? Then what will happen is that we can protonate this acetone and this alcohol intramolecularly. We can get the hemiacetal. Okay? We generate this hemiacetal, we move the hydrogen, the proton here, we put the proton, we move the proton from this oxygen to this oxygen. Why? Because I want to do a good leaving group here. Okay? When I have a good leaving group, what is happening is okay, I have this compound, I generate positive charge here because I remove the water, and basically what I do is a E1, and what I get is this compound, this double bond. Next step, basically I protonate the other carbonyl, and I do exactly the same as before. I am transforming this carbonate this alcohol in a very good leaving group, and it's leaving. I put R here in order to don't need to draw all this group. Okay? The water is leaving, I generate this carbocation, and then again E1 elimination, and what I get is the furan and this will be the final compound. Okay? This will be the final compound. Again, what I did is we have to check the functionality that we have and check what reaction we can do with the reaction conditions. In this case, we have an acetal with HCl and water. What we can do is to remove the acetal to form the diol. When we have the diol, this can react intramolecularly to form this hemiacetal. We lost water, E1 elimination to generate this double bond, and then we degrade the other alcohol, forming water, E1 again to form the furan. And the formation of the furan basically is the driving force of the reaction. Okay? Because the aromaticity, the stabilization that we get with the aromaticity is what is pushing the reaction to the final compound. Next one. here, a furan, and we treat it with carbaldehyde, formaldehyde, dimethylamine. These are the typical conditions for amanics. That means that first we will have the condensation between the formaldehyde and the secondary amine. We will get this intermediate, and then basically this position is highly electrophilic. We have a furan ring that is a nucleophile, a good nucleophile, and what is happening is that this is having a electrophilic aromatic substitution. And remember, the orientation of the furan rings always is C2. That means that what we will get is this final compound. Okay, that's here, this one is going to the nitrogen, and we generate this compound. Okay? The second one is a little bit more complicated, but what is happening? We have the furan, and now we are treating with furfural in HCl. What is happening in the furfural will be protonated, okay, and then it's happening exactly the same than before. We have the tag, we form okay, and now what could happen is that we are in acid media and we have chloride, basically a protonation of the alcohol we can form chloride, we can form the carbocation, because water is a very good living group. We form this carbocation, okay, and then the chloride attacks to form the final compound. Okay? Next one, basically now we have a pyrrole, and we treat it with, this is a migration, okay, and we have to decide where is happening the migration. How we can do it? We know that the nitrogen, the pyrrole ring, because it's a nitrogen heteroaromatic, is orientating at C2. Okay, that means that it's orientating to this position, only because it's a pyrrole. And then we have a methyl that, because it's an electron donating group by induction, is orientating ortho-para. Ortho, meta, para. Remember that always when we are counting the carbons, what is the position of the carbon, always has to be through the carbon. We cannot say ortho, meta, para. This is not possible. We cannot go through the heteroatom. Always over the carbon chain. Ortho, meta, para, that means that the orientation is here and here. Then we have that this position has the orientation of the methyl, this position doesn't have any orientation, and this position has the orientation of the methyl plus the C2. That means that this will be the most favorable. What we will get is basically the nitro in the C2 position.